Okay, we finished up yesterday looking at the measured components, and I mentioned to you that in your text there you have a page and a half of what we think are carefully reasoned arguments as to why you should probably measure more than one coil component. Again, it was directed at surveys with large fixed loop. But one area where we think often advisable to make measurements of three components is when you're doing central loop sounding. Big question when you're doing central loop sounding is, do you have any lateral inhomogeneities nearby? And of course you can detect them if you do a lot of central loop soundings, but part of the idea is not to do more than you have to. And if you do the sounding with a three-component coil in the center of the loop, and if you get X or Y components, assuming Z is upwards, if you get X or Y components that are significant compared to your Z component, then you know you may well have a problem and you have to check further. For example, Mike Wilt shows that if you're near a contact, you'll get, when you're near enough to the contact, the vertical contact, so that the X or Y components are of the order of 20% of the vertical component, then your sounding from your vertical component is just on the edge of starting to be distorted. So it's a very quick way of checking whether or not your vertical sounding is being contaminated by lateral changes in conductivity. Okay, borehole probes. What do you do with borehole probes? Well, try and avoid them. You have three choice. You don't have much choice. Well, we're not sure, as we mentioned last night after the meeting. You generally use ferrite down the hole. Ferrite down the hole seems to have worked quite well for axial component boreholes. Ferrite has problems. In a borehole, you don't normally put the probe too close to the transmitter wire, so you're usually fairly safe from those problems, which arise in regions of high field strength. When we start making X and Y components in the borehole, it looks like we start to have problems with ferrite, and we're just addressing those problems now. Question is, how do you tell the phi rotation of your probe? The initial way of doing it was using the primary magnetic field that was started by Krohn. It looked reasonably successful in Canada, but there's a move away from it. It looks like gravity is that is a pendulum is probably the best way of doing it. Gyros look attractive on paper, but they're very expensive. We don't think too many people are willing to put 15,000 bucks worth of gyro down the hole, and gyros are still gravity stabilized, so basically they do drift, and you're still relying on a pendulum in essence with your gyro. So gravity looks like the way to do it. Sources of noise. There are lots. Electronic noise is the preamplifier noise in your system. In a well-designed time domain EM system, you should not see the electronic noise. You should have a coil with large enough, a receiver coil with a large enough turns area so that external noise, whatever it be caused by, swamps the receiver noise. If you're looking at receiver noise, you have too small a receiver. And obviously the external noise goes up and down, so you have to be careful that in times of low external noise or places of low external noise that you're not settling down into the receiver noise, because then you're not getting the best value out of your receiver. External noise, typically spherics, RF transmissions, and there are various ways of trying to get rid of it. Power lines we see as two sources of trouble. One is that power lines, of course, act as huge antennas. They pick up everything for miles, including VLF, including radio broadcasts. And of course, if you're doing a survey with your receiver near a power line, you pick it up directly. Power lines as targets. If you've got your transmitter located close to a power line, you'll energize the power line and you'll actually see transient response from the power line itself. A difference between power lines and other targets is that I said earlier, and Alex has said as well, that targets in the ground consist of resistors and inductances. Once you get power lines, you get capacitance as well, and the result is that if you energize the power line, it actually starts to oscillate. It oscillates at some frequency, audio frequency probably. That frequency is not in synchronism with your gates, so what you see is noise on the different channels. If this is the undisturbed decay, you may see the data look like that. And what you're seeing here are the sampled oscillations of the power line. The way to tell whether you're seeing power lines as targets is to repeat the measurement, because you obviously energize the power line in exactly the same way. And if you keep getting data like this, you know that you're seeing power line oscillations, and you have no choice really but to move your transmitter further away from the power line. Pipes, I discussed, yes I did, in the galvanic current component bit. Pipes are a problem because you see them as galvanic current component. Couple of choices there. You can either take an EM31 and go running around looking for the pipes near your transmitter, or else just keep a very close eye for apparent problems in your data. And item number F is deck chairs, the well-known deck chair source of noise. We had one guy who was doing sounding sitting on an aluminum deck chair by the receiver coil. You have to remember that these coils are really, really, really sensitive. If you put a coin on the side of the coil, you'll see it, so you can't put a deck chair there. Noise rejection schemes. Choice of base frequency is important, particularly in the case of power lines as noise. We choose our base frequency so as to integrate out the huge signals that we get in North America as a result of power lines. So we just stack out an integral number of cycles of the power line. Normal stacking, where you just keep adding the data sequentially for perhaps your measurement may take as long as 15, 30 seconds. During that time you've sampled, depending on your base frequency, hundreds to thousands of samples. And if you have a very, very linear system, stacking really works. It's one of the best, one of the simplest ways of reducing your noise. You can try limiting spherics. That's usually not terribly successful. Better is to excise them all together. And to do that, you take your transient data, plot it out afterwards, and just look at each transient and just throw out the parts of the transients that are stricken with spherics. We've tried subtraction schemes for getting rid of 60 cycles. It usually doesn't work terribly well, and the reason for that is that the actual phase of the 60 cycles varies with time depending on the loading of the circuits in the power line, and so you have to make the subtraction schemes adaptive. They have to adjust their properties as the 60 cycle axis moves along compared to your base frequency. Selective filtering. I heard last night that you people use selective filtering to get rid, for example, of VLF. Our own experience has been that you usually make matters worse because the selective filtering rings when it gets hit by a transient, and you do get rid of the VLF, but you start introducing other sources of noise. One of the best techniques we've found for improving your signal-to-noise ratio is to do 3 or 4 measurements. If you're at a measurement site, instead of just doing one long measurement, do 3 or 4 short ones, and then you can look at the data, and if one of the soundings or one of the measurements is significantly different from the other 2 or 3, You just throw it out. And it gives you a very, very much better degree of confidence in your data. And we found that really, rather than doing complex studies on the statistics of noise, it's simply better to take several measurements and heave out the poor ones. Okay, the last section, strange effects. Thanks, Peter. I'll discuss the effects from homogeneous half space and conductive overburden. And basically, the problem which I will address is how the drive EMF in the target is distorted by the effects of the surrounding host rock or conductive overburden. As by now everybody knows, we work very diligently to get a nice ramp turnoff, get a nice rectangular pulse of EMF in the ground, but the ground is never that friendly to us, and we'll see that conductive host rock delays and broadens the drive pulse substantially. We'll see that it can alter the spatial components, and we'll see that it can alter the target response as well. We'll briefly address the question of IP effects and also of sticky susceptibility. So dealing first then with the drive distortions. Again, here's my here's our original slide showing a typical, at least in North America, but also down here in essence, survey scheme. We originally assumed that the ground was perfectly resistive. We're now going to examine what happens when we let the ground have finite conductivity. In free space, again, you have your ramp turn off and a nice rectangular pulse driving the response of the target. To introduce the subject, I'd like to show you a cross-section of what the field in free space looks like from a large loop transmitter. This is a section. The loop is sitting out like that. It's 400 by 800, no, 3 by 600. These calculations were actually done by Jim McNay. And I want you to focus your attention on this region here where the primary magnetic field is horizontal, no vertical component. Again, this is a free space primary field plot. We saw earlier that in a conductive ground that the current diffused downwards and outwards with time. Clearly, if we have a target down in the ground here, for example, in the case of a conductive ground, as soon as we turn off the primary current in the transmitter and reduce the primary magnetic field to 0, what's the magnetic field down here? And the answer, of course, it's exactly the same value that existed before you turned the transmitter off. So what excites the target in a conductive ground? It's not the act of turning off the transmitter. Turning off the transmitter sets up currents in the ground. And of course, the target is excited by virtue of the changing magnetic field from these currents as they roll down past the target. So instead of having a nice rectangular pulse, we suspect that maybe the magnetic field from these currents is not going to look so nice. And I show here calculated values of dBx by dt and dBz by dt at the point which I showed you on the free space diagram of the magnetic field components. I calculate dBx by dt, and I'm interested in it now because it's a measure of the drive EMF in the target, which was rectangular, but now looks like this. The scale here is the product of rho t, and the vertical scale is normalized dB by dt. And what we see is that Bx dot, which is again the drive EMF for the target, is initially 0, rises to a peak value, and then falls fairly slowly with time. The actual time scale is dictated by the ground resistivity. In the case where the resistivity is very high, this scale represents very short times, and basically this starts to look like a delta function again, which when convolved with your ramp gives you square wave excitation. If the ground resistivity is fairly low, these times can be quite appreciable, and all your work in trying to get the ramp as narrow as you can be lost, because in 10 ohm meter ground, for example, the width of this drive can be several milliseconds, so very, very much larger in general than your transmitter ramp. Also, it has a decay which goes on for an even longer period of time. On the next slide, I'll show you what happens when you convolve that with an exponential decay. Okay, Bz dot looks like this. And you'll remember that in the earlier slide that I showed you, the horizontal field, or the magnetic field, the primary magnetic field at the measurement site was horizontal only. And yet this slide shows that Bz dot is certainly not 0, and in fact its peak amplitude is about half that of the x component. How can this be? And the answer is that at any instant of time, the vertical field for sure, or Bz dot, is for sure not equal to 0. But what is 0 is the area under this curve, the net area of this positive part and this negative part. So if your ground is extremely resistive, this vertical component of the drive goes buck buck like that and essentially is 0, so you don't notice it. It doesn't excite a horizontal component of current in your target. But in the event again that the resistivity is fairly low, this thing is very appreciable, and it means that what happens is that the first part of the drive induces currents in this direction in your target, and then the drive decides it made a mistake and turns around and starts inducing currents like that. And the net result is that you will have current flow in your target from the presumed 0 vertical field component. And this effect is seen. It's been seen in boreholes where you'll see the reversal of the drive on the target. Okay, in the next slide, as I say, I'm going to convolve this drive with a target with exponential response. And what we're going to see is that if the time constant of the exponential response is much larger than the width of this drive, it acts as a delta function, and the fact that the drive has been broadened doesn't make much difference. But if the time constant of the target starts to get comparable with this width, then basically what you see, instead of seeing the exponential decay of the target, you see a replica of this drive function. So in conductive ground, even though you've got a nice plate with single exponential behavior, you may never see it, because if the time constant is small enough, you'll simply see the drive. Is that clear? Partly. Okay, so again, I have a linear scale here, a log scale there. The dashed line is that drive that I showed you, this time plotted on a log-lin scale. If I have 100 millisecond, that's supposed to be time constant, and I hit it with this drive pulse, no problem. The width of the drive is narrow enough so that it just hits the target, and you get a nice exponential decay after the few milliseconds of the width of the drive. As the time constant of the target gets smaller and smaller, still exponential decay, the initial amplitudes start to fall a bit. Once the target time constant starts to fall, in this case below about 2, and this is done for 10 ohm meter ground, so it's very conductive ground. Once the target time constant starts to fall below about 2 milliseconds, and specifically for 1 millisecond, instead of getting exponential decay, what you're getting is really just a replica of the drive. So the three effects of a conductive host rock are that it delays the drive to the target, it broadens the EMF to the target, and it can alter the spatial components in that in a place where you should have a zero field component in free space, those currents actually can give you a much more complicated drive than you would suspect from free space values. Same is also true for a conductive overburden. Here I have a dipole transmitter. I have an overburden of 3 Siemens, which by your standards is not too impressive. And I have a plate target over here. And if I am in free space, what I've plotted here is the primary EMF that would exist in the absence of a conductive overburden. That's the amplitude of the primary drive. So at 100 meters depth, I have dB by dt of this value, in other words, an exciting voltage of that value, exciting EMF, and it varies with depth. But it varies reasonably slowly over the target so that we can, to a first approximation, assume that the horizontal magnetic field, or more accurately its derivative, and thus the inducing EMF, is relatively uniform over the whole target. If, however, I put my 3 Siemens overburden in place, obviously, once again, when I turn off the transmitter, what does the target know? The target knows nothing. It doesn't know the transmitter's been turned off. What that does is to excite currents in the overburden, and as we discussed earlier, those currents go out linearly with time with a velocity which is dependent on this conductance. And once again, it's the changing magnetic field down here as a result of those currents moving radially outward, which generates the EMF which excites the target. And I show here at 3 depths, 50, 150, and 300 meters, 50, 150, and 300 meters, what that exciting EMF looks like. And at 50 meters, we see that it's very complex. At the instant the transmitter turns off, those currents start moving out, and the EMF in the target at a depth of 50 meters starts off with one sign, goes through a crossover, reverses polarity, and then slowly decays. At 150 meters, it's a little bit better. It starts from 0 and goes to a peak and decays. At 300 meters, it's different again. Now the inducing EMF suddenly shoots up to a finite positive value and slowly decays. Well, your total current flow in your target will be the result of that excitation integrated over the target, and clearly it's going to be very different from the excitation in the absence of the conductive sheet. So once again, there can be quite significant effects in the excitation of the target from the conductive overburden. And for sure, you guys see these effects in your surveys, okay? I mean, that's not a very conductive overburden compared to the numbers that I've been hearing down here. Okay, IP effect. I'm rattling through this fairly quickly. It's more or less to show you that it's in the tables there, and if you're interested in further discussion, we can discuss it in more detail. Here's a cross-section of the transmitter on the ground coming out of the page. As is by now fairly well known, the electric field associated with the transmitter when it's turned off basically charges up the ground. We can think of, in a simple way, the ground consisting of a lot of little capacitors aligned in the same direction as the transmitter wire. And when the transmitter turns off, the initial electric field charges up the capacitors. It's usually a fairly slow process, and what happens is that those capacitors retain their charge. The induced currents do their thing. They decay downwards and outwards, and then sometime during the transient, these capacitors start to discharge, and the problem is that they give you a changing magnetic field which is in opposite direction to that from the currents in the ground, because the discharging capacitive currents are in the opposite direction. And if you're doing surveys with a single large loop, for example, and you have the IP effects, this is the undisturbed response at some late time when the currents are out here somewhere. This is BZ dot. When you have the effect of IP, it's usually fairly close to the actual wires themselves. And what happens is that the field that you see in the presence of IP looks like this, and you can fairly simply show that that's the response from those little currents in the vicinity of the transmitter wire discharging in the opposite direction from the induced currents in the ground. And so you get a crossover in the Z component as you go by the transmitter wires. More seriously, in the center of the transmitter, you can get a significant reduction in the magnetic field that would have existed, or dB by dt, in the absence of this effect. This effect is relatively common, and so quite often with large loop transmitters, you'll see it. Yeah.
Discharging the capacitance, how rapidly does that take in relation to your time constant?
Variable, okay, variable period. And the problem is that the IP characteristics of the ground, and this has been studied a lot by Lee down here in Australia. There are a number of really good articles on the subject. The problem is that it's a function of the Cole parameters of the ground, the conductivity, the chargeability, etc. And the time domain chargeability, if you like, or the time domain response occurs over different ranges of time than the normal IP response. So ground that you wouldn't think would give you a problem can give you a problem. And it usually arises probably from clays and that sort of thing. It's not really a major problem when you're doing large loop surveys. It is a problem when you're doing moving loop surveys or soundings, because it can be pretty hard to identify. There's an error in this slide. It's supposed to be the log of BZ dot T, and it shows you a time decay response in the absence of IP and in the presence of IP. And you'll see here that the way I've drawn it, that at early times the capacitors haven't started to discharge. At this time they're doing their thing, and at late times they've disappeared again. You can get a whole variant, a whole series of responses, and as probably well known to many of you, this response can actually go negative. These IP responses can be pretty large. How do you avoid them? Again, I showed that the effect was nearest the transmitter loop. They are primary field related. It's the primary, turning off the primary field, which charges up the capacitors. So the trick is to make your measurements as far away from the transmitter as you can. And for that reason, for example, if we're doing soundings, very often we'll do a central loop sounding, and then we'll do a second sounding with the receiver outside of the loop in order to see whether, excuse me, some Aussie bug, to see whether we're being affected by it. It's a problem, and you should be aware of it. Okay, I think that probably we'll let this one go. There are various survey configurations. Those of you who need to know about them know about them. We do use large loop soundings, and this slide simply shows the depth of exploration that you can get using various large loops as a function of the upper layer resistivity. This is the depth. And basically, one interesting feature of these curves is that you can show that the depth of exploration is relatively insensitive to the resistivity of the upper layer. For central loop sounding, it turns out that the depth of exploration is a very nonlinear function of the transmitter dipole moment, and you fairly quickly reach a limit beyond which near zone sounding techniques are not a good idea, because you simply need a very, very large transmitter loop to get down to depths of the order of 3 kilometers or further. Okay, I think that we'll let it go at that. I've already discussed integrating back up the response curve to calculate B of t. I'll show you some survey data. That's simply an example from Newmont where they've integrated the data and contoured out the horizontal magnetic field. And you see that you get nice peaks in the contours, presumably over the axis of the conductor. The B versus B dot argument is shown in Kalari. We have here a fairly deep, 500 meters, flat-lying, not very conductive target. And I'll show you the responses as we go over the target. First of all, measuring dB by dt. Secondly, measuring dB by dt, but corrected for the transmitter turnoff time, which makes it a true impulse. And thirdly, what happens when you integrate the data. This is the raw survey data. We plot the data out in groups of channels, each one linearly plotted out with different scales between each group. And you'll see I've got 1, 2, 3, 4, 5 groups of channels to cover the dynamic range of the signal. This upper scale is 300 millivolts. This lower scale is 3 millivolts between the survey traces, so there's a factor of 100 to 1 difference in the range. You'll notice the little glitch here, which is due to a conductor probably sitting near the transmitter wire, because that's the transmitter was. And you can see that at early times, the little glitch is pretty large. It's an example of 1 over tau e to the minus t over tau, where tau is small. The glitch decays very quickly, but its initial amplitude is large. Here, it's about the same size as the target response. After 8 or 10 channels, it's disappeared. The next slide shows what would have happened if we had actually managed to get the turnoff time 0. That's the first set of data converted to delta t equals 0. And now you can see the glitch is huge compared to the early channel responses. However, as it did before, it decays within the first 10 channels or so. Okay, and the next slide shows what happens when you integrate the data. As I say, try it. I think you'll like it. Because, first of all, you see the glitch has just about disappeared. And secondly, instead of having 5 different panels to show the data, and this is linear scale, this isn't your horrible log plots. You only need 2 panels of data to show the whole profile. I think that's pretty attractive. And there's lots to be said for linear presentations of your profiles. Okay, the one thing I'm not going to talk about, if you have very good conductors, if anybody's interested, I'll talk about it afterwards with them. If you have very good conductors, the question is, can you see them with off-time systems like this? And the answer is no. Because of the 1 over tau e to the minus t over tau, As the time constant gets very long, the initial amplitude gets very low, and you can't see them again because there's no EMF induced during the off time. However, with these systems, you can actually make a measurement during the on time, and we do that. And so you can detect infinitely good conductors with an off-time system like this and any of the other systems, as long as you have the facility for making a measurement during the on time. Good, thank you. Are there any questions? Or Alex?
Examples where the impulse systems haven't detected a good conductor?
I'm sorry, say again?
Have you seen any field examples where the impulse
my many good friends at INCO would say that they exist. They're dealing in the borehole with huge big targets. They actually use UTEM, which I think is sort of silly too. I want to know why they don't just lay a big loop and energize it at 1 hertz and just measure the field. They use the UTEM to do it. They have to correct for the primary field, and they're looking at 5,000 Siemens targets, that sort of thing, and they say that they see them better on the UTEM system. They would also see them had they done the 37 and measured the primary pulse in just exactly the same way. Because to see those very conductive targets, you basically just make an in-phase system and calculate out your primary field.
How do you measure the primary pulse, the DVT?
I'll show you after, okay? Easy. And it works.
The dry effects sort of help us because I've certainly modeled plates on responses that have conducted, that indicate sort of plate conduction system, drilling at the order of 10,000 feet.
The question was, do I think the drive effects help you?
Yeah.
I think they don't much matter in that case. If you have a very, very conductive target, even with a conductive host rock or conductive overburden and substantial distortion of the drive, it still acts essentially as a delta function as far as the target's concerned. So I wouldn't expect them to have much effect.
Study behavior of electromagnetic field in conducting medium. So at the beginning, somewhere at the beginning, we discussed behavior fields confined conductor, our targets in mining perspective. It's not only one target. Then I started last time to study behavior of the field in surrounding medium. As usually, first of all, frequency domain, time domain. And it's interesting to see, are there common features? Or is there difference between them? What I'm telling you, it's not simply a tale about fields. That's how that's difference in behavior of these fields explain why we moved from frequency methods mainly to time domain methods. So it's not too bad only to accept fact, but it's proper to accept fact, but it's not too bad to also to understand why it happened. Why it happened. So I took the simplest example, uniform conducting medium, magnetic dipole, transmitter, receiver, and took arbitrary point P and wrote yesterday expression for current density. Currents create field, so it's important to know how these generators of the field are distributed. And wrote simple expression, current density at frequency domain. Time domain we will come. Frequency domain at some point P, not P is not good point because parameter P, induction number, point A frequency is equal I gamma mu omega m 4 pi r square EKR unit minus EKR and not too bad to write sinus theta. Now, so, and we came to conclusion yesterday from pure mathematical point of view, then recalling what we discussed before, all this term has very strong physical meaning, very strong physical meaning. What is it? Current density caused by primary electrical field. But all this term is current density at each point caused by primary electrical field. So let me call it I naught equal, I will write magnitude only, gamma mu omega m 4 pi r squared sinus theta. So if we are not, when it happens, when induction number, we discuss it, distance over skin depth less than unit. So it's from engineering point of view, it's not too bad to understand around transmitter, whether it's current loop, whether it's small loop, large loop, in frequency domain, around all currents which arise are practically equal primary conductivity times primary electrical field. As I mentioned, this expression, very simple, very elementary, does not have any relation serious mathematics, it's a pure engineering approach, but it became basis, the most popular method in oil logging industry, one of the most popular, without any doubts, induction logging. But this only one equation is the basis of 90% of theory of induction logging which is used widely. Now, also it's a basis, briefly told you, it's a basis of shallow profiling systems, EM31, EM34, and also we observe in other methods the same behavior. What is important? Important that around transmitter, currents are mainly defined by this term. So at each point, point A1, I would like to calculate current. What I have to do? Step number one, take primary electrical field. Do we know it? Yes, we do know mu omega m 4 pi r squared sinus theta. Now, what we have to do next? Multiply by this electrical multiply this electrical field by what? Where? Here, here, here. No, at the same point. So gamma E naught. So all two operations are extremely simple. Now step number 3. I would like to calculate magnetic field, for example, in receiver. What I have to do? I have a current. I know its density, current density. I have to calculate current, dI equal J ds, and then using Biot-Savart law, calculate magnetic field. Now, I would like to calculate current at another point. What I have to do? No difference. But what is interesting, nobody told you have to assume that conductivities are the same. So this method of calculations is applied for horizontal layer medium, for medium which in borehole, in formation, etc., etc., etc. I will return back to this expression. I only wanted to tell a few words about it. Then I will, when we will start to discuss different soundings, time domain, frequency, and geometrical, I will come back to this expression. Now, let me point out something else. This current is in phase with current transmitter or shifted? Huh? Sorry? This current. Why do you think is in phase with current in transmitter? You have current, changes cosine omega t, correct? Its magnetic field, primary magnetic field changes as cosine omega t, changes. But primary electrical field arises due to magnetic field or rate of change magnetic field with time. But that's the point, rate of change. So it must be shifted by 90 degrees. So we are talking about out phase or quadrature companion. By the way, the most popular companion for many years in inductive methods of mining prospecting. So around transmitter, there are many currents which are shifted by 90 degrees, which are proportional conductivity frequency and defined by only primary field. How nice, how simple. No any complicated equations. Now, why it's here frequency? Because primary electrical field is proportional to frequency. Why it's conductivity? Because Ohm's law. So always, without any exception, around transmitter, quadrature component of currents, always proportional conductivity and frequency, no exception. But magnetic field, according to Biot-Savart law is calculated. So quadrature component of magnetic field is also proportional frequency and proportional conductivity at the low frequency part of spectrum when this range is small. Summarizing, I would like to tell, so first of all, around transmitter, I mentioned yesterday, around could be 50 meters, could be 10 meters, could be 5 meters, depends on conductivity and frequency. There is an area where there is a quadrature component of currents. They are shifted by 90 degrees with transmitter, by definition, proportional conductivity and frequency. What is essential, at each point, current is independent on currents at other places. Is independent, that's vital. In other words, it's defined by only transmitter. So mathematical simplicity goes along very well with physics, with what is for us important. Now, shortly we say there is no interaction of currents inside. Now, let us consider general case. That's most interesting. So let us recall, it's not current, it's complex amplitude of current. It has, it has real part plus imaginary part, correct? Still does not have any physical meaning, but as soon as we will say current equal real part A plus IB times what? No. Not everything real and imaginary, but what is our iron rule? How to find field if we know complex amplitude? Huh? Oh, very good. Multiply by exponent and take bravely real and imaginary part, correct? So, you remember this lovely Euler formula? I omega t is cosine omega t plus I sinus omega t. Multiply two complex numbers, take real part, and you will see it's equal A cosine omega t I don't pay attention now, sine B sinus omega t. So real, and imagine that's our in phase component, that's our amplitude quadrature component. So this number contains all information about both components. Now I will do the following. I plot graphs using this equation, two graphs. Current, here distance over skin depth, or by definition R gamma mu omega over 2. Here I will do the following. Quadrature component of the current quadrature divided by current I naught. I naught is our approximation when range of small parameter. I will write again in order to remove misunderstanding. Gamma mu omega m 4 pi r square sinus theta. And also graph of in phase component current divide I naught. How I am going to derive? From simple equation which I wrote on the top. Exponent, unit minus kr, I calculate, take real, take imaginary, simple matter, and now let us look what would happen. Tell me please, let us start to consider quadrature component of the current. Here, ratio, induction number, distance over skin depth. What do you think? What would be here? So we pay attention this graph. So what would be ratio between quadrature component of current at any point, normalized by current and range of small parameter when parameter is small? 1. Why? Because we demonstrated when small induction number quadrature component exactly coincide. So graph starts from 1 and it goes in this way. Now let me show you what happens within phase component. Again, I derived it from very simple, it's impossible to find simple equations here. Now this graph will have this behavior. That's in phase component of current. In phase component current divide I naught. That's quadrature. Let us read this equation. Again, in order to remove all misunderstanding, current at each point equal current naught I EKR unit minus EKR. So what I did, I expanded real imaginary part and plot this graph. So it's time to discuss how to treat this equation. First of all, physics. My dipole, arbitrary point. Again, I consider uniform medium, but it's true for overburden, for Hall stroke. Only equations more complicated. That's it. Let us took arbitrary point. What this equation tells us? At each point of the medium, but that's dipole, that's point, there are how many currents? So, picture. Dipole, medium. What is the current loop inside of each medium? What is shape? Circle. Here circle. Center here. Here circle. Here. So mentally imagine many currents. It doesn't matter, frequency or time domain. You will have this system of currents. Now, let me ask you a question. How current changes? Here current changes in transmitter I cosine omega t. How here current changes? Sorry? Sinus omega t, but some phase shift. So here we have arbitrary place amplitude, some A cosine omega t plus phi. Amplitude of current depends where we consider our point. Oh yes. Phase depends. Yes. Now, how it's reasonable, what we are doing, instead of this presentation, I pointed out, I mentioned once, we present it how? As A cosine omega t plus B sinus omega t. So what these graphs show? This graph show behavior in phase component and quadrature component. That's all. Magnitude of in phase and quadrature. Let us read these graphs. So first of all, back to my suggestion, it's very useful in frequency domain to imagine at each point of the medium two currents. One changes synchronically with current in transmitter, another shifted by 90 degrees. So mentally imagine, that's very, very good. Why it's good? Because what we would like to know, how this part of the medium, when there is this current, affects on our measurements. How it can affect? Through magnetic field, which is caused by this current. Quadrature component, current create quadrature component of magnetic field. In phase component, create in phase component. If I tell you, let us forget these graphs. At this point, that's my transmitter, that's my point. At this point, there is no in-phase component of current. Clear? Suppose. Only quadrature. This current does create magnetic field in receiver? It does. Which component it creates? According to Biot-Savart law. Quadrature. So from this ring, current ring, this part of the medium is not seen measuring in phase component if in phase component is absent. But you see it measuring quadrature component and vice versa. So you will see after a few minutes that depth of investigation in frequency domain depends what you measure. What you measure, not from geometrical point of view, but electrical. You have fixed transmitter and receiver, and I will explain you that quadrature in phase component of magnetic field may have completely different depth investigation. Moreover, I will show you that measuring, if you can measure in phase component, you practically can get the same result as in time domain. And we will destroy Zerotherm, Geonics, and all other companies that develop here measuring in phase component method. So it's not too bad to understand these facts. So let us start and see what these graphs show us. Ready? Do we know current I know? That's fine. That's very simple expression caused by primary field. So let us read. Suppose I fixed frequency. Suppose I fixed conductivity. Therefore, this graph shows what? Can you help me? If we fixed frequency, if we fixed conductivity, what does this graph show? Change of current density with distance. Correct. Not only depth, in any direction, including depth. So what we see, when distance is relatively small, what does it mean relatively small? Nobody knows nobody measures in millimeters, centimeters, meters. When skin depth, distance over skin depth less than unit, skin depth, again it could be 100 meters, it could be 10 meters. So as soon as distance much smaller than skin depth, then which component prevails? Quadrature. So around you there is a quadrature component. In phase component is extremely small. Again, when I'm telling this story, I don't think really about current. I think already about magnetic field which is caused by these currents. That's important. Now, at the beginning, as I told you, quadrature component is practically defined by primary electrical field. That's simple approximate theory which is in many cases works beautiful. Then what happens with increasing distance? With increasing distance you are going away from transmitter. Therefore, primary electrical field becomes relatively smaller. And therefore, current density somewhere here depends not only primary electrical field but also secondary due to other currents. Other currents, also induced currents, create magnetic field. It changes with time, and then already I cannot say this current is due to primary electrical field. This current. It's due to primary and secondary. What does it mean secondary? You have many currents. Again, what I'm telling, it's true for time domain also, no difference. You have everywhere currents. Near transmitter, these induced currents also do create secondary electrical field. But primary is dominant. But you are moving away, and you start to feel influence of secondary current, induced currents, which create secondary magnetic field. Their change creates secondary electrical field. So we say in these cases, oh, we observe interaction between currents. And interaction is such that finally, far away, no quadrature component of currents. Very small. So the low frequency, the higher resistivity, what happens with range where currents equal I naught due to primary field? With a decreasing frequency, with increasing resistivity, what happens with domain where currents only define primary field? Becomes bigger. And you see this interaction so far that you will never notice. Vice versa, if you increase conductivity, if you increase frequency, the zone will be absorbed relatively close. Now let us look another component. Now, just a second. What common sense tells us? If I have transmitter and receiver, and if receiver is done in such a way that it measures out phase or quadrature component, can I expect great depth of investigation? Because magnetic field is caused by quadrature components of currents. Where there are? Near. So I have to expect, I cannot have right to expect great depth of investigation. It looks like measuring quadrature component, if that's true. It's caused by mainly area around transmitter and receiver, not far away. Now, let us pay attention before in-phase component. Let us look in this graph from different point of view. Let us fixed point of observation. You have receiver which measures current, ampere meter, at different frequencies. This graph shows you how quadrature component changes with frequency at any point. 2 points of view on this graph. Now here's something interesting. First of all, there is a maximum. Maximum takes place at certain value R over delta. Let us remember it. Now, near transmitter, is it possible to compare quadrature in phase component of currents? No way. So near transmitter, in phase component of the current, is very small. Always. If you use inductive method excitation loop, small, large loop, doesn't matter. Now, this area, you can imagine, could be very large. It depends on skin depth. So what does it mean? It means if you decrease, let us say decrease frequency, where this maximum, if you decrease frequency, where you will observe this maximum? Close to transmitter or far away? Far away. So it could be in very large distance. It could be 50, 100 meters, 10 meters, depends on conductivity. Or if you increase resistivity, you are working in more resistive medium, where this maximum would be observed? Far away. Vice versa. If you took very high frequency, your medium is relatively conductive, this maximum will be close. Now, what does it mean? It means the following. If you measure instead of quadrature in phase component, you don't feel practically what is going on around transmitter and receiver. Understandable? Because no currents around transmitter and receiver. So it's a dead, silent area. For instance, you have overburden. You have transmitter loop and receiver. If frequency is low enough, no in-phase component of currents where? In overburden. If no currents, no influence. Because only one necessary requirement to get influence is to have currents, because we measure magnetic field. If we would measure electrical field, that would be different story. If due to the electrode. But we measure magnetic field. If no sources magnetic field, no magnetic field. So at sufficiently low frequencies, at sufficiently resistive medium, or one condition is enough, frequency or resistivity or both, overburden becomes transparent. That's what we would like. And many practical examples does show in airborne, etc., that in phase component less sensitive to change thickness of overburden as with respect to quadrature component. So now, as you remember, with increasing frequency, decreasing frequency, this maximum goes away from transmitter. Therefore, decreasing frequency, we increase depth investigation. Now, where is the separation between transmitter and receiver? No. You can take transmitter. We are trying to understand physics. We are not talking about some real systems. We take transmitter, we take receiver, distance 1 meter. Suppose we are smart enough, we can compensate primary field. So we don't speak about, we speak about physics. So if we are close transmitter to receiver, what happens measuring quadrature component? We will mainly measure quadrature component of currents near transmitter. Depth investigation will be practically 0. Now looking in the phase component. Where currents? Far away. Why we have to make large separation between transmitter and receiver? You can measure where you practically your transmitter if you can cancel primary. So this consideration shows that both components have completely different depth of investigation. Please imagine the same transmitter, the same receiver, the same frequency, 1, not 2, not 3. Only in one case you measure one component, another case another component, not geometrical. Geometrical, for example, BZ or BY. You measure different electrical components. Electrical, I mean outphase and quadrature. One of them changes as sinus, another changes as cosine. And we get completely different depth investigation. What really we observe here? Changing frequency. We observe diffusion. We don't observe diffusion when we measure quadrature, because there is a primary field which does not allow to see it. But primary electrical field which creates I naught. But when you see in phase component, you see diffusion. So nobody told you always we have to work in time domain. There is another scenario. Measure in phase component, you practically will get the same result as in time domain. Now, are there questions? No questions?
So what ratio of R index gives you the maximum?
Where is the maximum? Where is the maximum? It's around 1, 2, not 10, not 20. Open my green book, you will find numbers. Even I can help. Or maybe not help, I don't remember. Do I have number or not? After 5, 6 days of lectures, I don't remember not only this one. No, I don't have it. I have only for time domain. Between 1 and 2. So my goal is achieved if you remember the following fact. You have transmitter loop. You are working not time domain, in frequency domain. At the point of observation, if you measure both components of the field, they have completely different depth of investigation. And it happens due to the fact that completely different distribution of currents, which changes sinus omega t and cosine omega t. Now let me show you graphs of behavior of magnetic field at observation point. For instance, suppose we have dipole and transmitter and receiver. Suppose we have fixed separation. I took example of logging system. No difference if we take this system or we take loop and measuring sand. Doesn't matter. Now, we know, for example, for component BZ, I gave you last time, mu naught m 2 pi L cube E AKL unit minus IKL. What I simplified, it changed. Instead of R, I wrote distance, A, separation. Now, cosine theta, but theta here, 0, cosine theta, 1. So that's a typical expression for correct typical expression, which is used for understanding induction logic, for instance. What is the meaning of this expression? Again, complex amplitude, of course. What is it? Primary magnetic field. Magnetic field at this point caused by current in transmitter. So let us, as usually, as always, secondary field compare with primary field. Then graphs for quadrature and in phase component will have the following form. Quadrature component magnetic field, normalized BZ, no, we don't need it, BZ, not primary field. Here in phase component of the field, oh, no, not good place. BZ not in phase component. That's in phase, that's quadrature. That's what we measure. Let us stop here and then I will continue.